Okay, so picking back up where we left off, I think we mainly had the domain and range to talk about, right? Okay, we had talked, and I don't have it labeled on here, but we talked about this whole, and we talked about asymptotes. Okay, so domain. Domain is our, what kind of values?
X values.
X values, right? And so with domain, we're going to read left to right. And so as we read left to right, or as we look at our graph, where does our graph start? Starts at negative infinity. And where's the first time it takes a break? At what X value? At -3, because it's going to run closer and closer to that asymptote and not touch it, right? So the first piece of my domain, negative infinity, because my graph is going off left to infinity, to the X value of -3. The X value of -3, because that is my vertical asymptote, so my graph is going to get closer and closer to -3, but never touch it. Parenthesis or bracket? Parenthesis, because we're never touching it. Then, where's my graph pick back up? As we move left to right, it now picks back up down here. So where is this starting? What value are we starting at officially? -3 again. We just don't touch -3. That's -3 with a parenthesis. And then, how far do we go? If it was without the hole, I would be right there with you, 3 to infinity. Because there's a hole, we have to include that hole. That hole happens at what? 3. So -3 to 3. It's a hole, so I'm using parentheses because it's not included. And then where does my graph pick back up? On the other side of 3 to infinity. Does that ring some bells? I know. You guys always complain about domain and range, but I hope it's getting a little easier. I was starting with domain and range right off the bat in Algebra 2. So, okay, range. Domain is X values left to right. Range is Y values, and we're going to go bottom to top, right? We want to say top to bottom. I'm right there with you, but we need to start low to high. So, where does my graph start? Starts down here going towards negative infinity. As we go up, my graph is going, my graph is going. Where's the first break I have? Is there technically a very tiny gap right here? There is. So we can't just jump up to the asymptote. There's a hole right here, isn't there? So there's a gap at that hole. The Y value of that hole is 5/3. Try that again. So negative infinity to 5/3. Yeah. 5/3 to 3, because you're going from the hole and then to the asymptote. And then it is, we jump over the asymptote. What Y value does my graph pick up back up on? Well, now we're on the top side of 3, right? So 3 to infinity. So I left out the 5/3 to 3 in my notes. And I'm wondering, because I check my notes against the key, and I'm wondering if she didn't have them in the key, or if I didn't check that. I don't know. Okay, that's all coming back, right? Okay, let's go work with some limit notation. That's the other thing. Because your notes are 6 pages, normally I kind of like to blow it up, make it big, and do half a page. I can't do that because I have 15 pages to split across 3 classes. In algebra and pre-calc, I teach both before and after you guys. So
That's where you go into it.
I know. I wish it was a little bit more. Now, I don't know if it's a memory thing or what, but okay. So we're going to talk about limit notation and how, understanding it. Now, we talked a little bit about limit notation yesterday, yes? When on the first page, we talked about proper notation and what that looks like. So now, we're going to revisit notation that you've maybe seen some in pre-cal. I'm trying to think how much we've used it. But then what we're looking at for calculus. So we're going to use this graph right here, which is graph is what we just saw on the front side. And we're going to put it in proper notation as well as fill in the blanks. So as x approaches negative infinity, the graph of f of x approaches what? So what I'm asking right there is as x is approaching negative infinity. So where is that going on this graph? As x approaches negative infinity, that's as the graph as we go to the left, yes? What is f of x approaching? And so when we ask what is f of x approaching, we're always asking what is the y value approaching? Okay, so our answer to a limit is always a y value. So as we go off to the left, so this is my leftmost piece, as I go off to the left, what y value am I approaching?
3.
I'm getting closer and closer to the asymptote at 3. Now, appropriate form, okay? In calculus, I would expect you to write the limit as x approaches negative infinity of f of x is equal to 3. That's the calculus. That's what's going to be expected of you. Okay? So get used to that form. Don't make it your own personalized form. Get used to this form. Okay? As x approaches positive infinity, the graph of f of x approaches what? 3 again? The only difference is it's 3 from the underside, yes? But in this sense, it doesn't matter. So as we go off to positive infinity, we are approaching 3 from the underside. So again, appropriate form, the limit as x approaches infinity of f of x is equal to 3. As x approaches negative 3 from the right, the graph of f of x approaches what? So as we approach negative 3 from the right, so what? Negative 3 from the right means I'm tracing this graph, yes? Where are we going? We're going down to negative infinity, yes? Now, I mentioned yesterday, so when we do this, the limit as x approaches negative 3 from the right means I put a plus sign in the superscript, okay, of f of x equals negative infinity. As x approaches 3 from the left, what are you thinking? No? Reread the problem. It's not as x approaches negative 3. It's as x approaches positive 3. So as x approaches positive 3, which is right here, from the left, what y value am I approaching? 5/3. Or in other words, what y value is at that point? And so it is 5/3. So the limit as x approaches 3 from the left means I put a negative in the superscript of f of x equals 5/3. If we write this limit notation enough times, it'll be burned into your head, right? Okay, now this is what you guys really wanted to answer last time. As x approaches negative 3 from the left, where are we going now? That's going to positive infinity. So the limit as x approaches -3 from the left of f of x is equal to positive infinity. And lastly, as x approaches 3 from the right, what are we approaching? Back to that 5/3. So the limit as x approaches 3, from the right, so don't forget the plus sign like I almost did, of f of x equals 5/3. Okay, so we're going to put some of this into words. Can you explain what the value of a limit represents in terms of the graph? So we're going to talk later in this lesson about using tables. Right now we're just going through graphs and how we read a graph. And looking at this, what is our limit? Our limit answers are what? What type of answers are our limit answers? They are, it's as x is approaching something and our answer is a y value, right? So when we talk about what does the limit represent in terms of the graph, it's that y value that we're approaching, okay? If we're just asked for a limit in general, it has to be the y value that we're approaching from both sides. Now, a lot of these were more specific, left or right, but it's that y value that we're approaching. In her notes, she talks a lot about it's the target value that we're aiming for, okay? Keep in mind the limit can also occur at a hole, which is the removable discontinuity, or an asymptote, which is an infinite or non-removable discontinuity. Now, what do you guys want me to write down there? So I have several things written in my notes. So I am going to say the limit is the y value, the graph is approaching, from left and right of the target's value. And the target value being that x value. Okay. Is that good enough? I think I'm just going to leave it right there. Okay. Write down whatever you're writing there. As we get to next page, yeah, we're going to practice a bunch of graphs. Informally, a limit is a y value which a function approaches as x approaches some value. Notice it says down there, the limit as x approaches c of f of x equals L. And that means as x approaches c, f of x approaches the y value of L. Now, I don't know that I've ever caught this, but they specifically mention that L needs to represent a real number. Okay, so that's just one of those little kinks, but L does need to represent a real number. And that will, very rarely, but it happens here in the notes one time, where that matters. Okay, so do keep in mind that L represents a real number. Okay, ready? So we have this lovely piecewise function graph, and we're going to consider it. We're going to talk about all the limits here. So, for example, say you want to find the limit as x approaches 4 from the right of f of x. The positive sign is the limit notation, indicates a right-hand limit. We've already talked about that. If you think of the function as a highway and imagine you are traveling along the path, which is the graph of f of x, towards x equals 4 from the right, not to the right, but from the right, and you stop at the vertical line x equals 4. The y value where you stop is 3, thus the limit as x approaches 4 from the right of f of x is 3. So again, if here's 4, hop on the highway right before then. As I approach that y value of 4, what x value do we end up at? And we're at an x value that is at a level of 3. Okay? So that's what we're going to practice here. We're going to use this graph and do parts A through N, which is a lot of problems really, but it goes quickly. Now, part A, f of 2. What's that asking me? What?
I don't know. My brain's jumping up to there.
Okay. What's f of 2 want? Is that a limit? Technically, is that a limit they're asking for? No. They just want to know what is the function value when x equals 2. So what is my function, or what is the y value when x equals 2? And what would you say here?
-1.
-1? I hope you agree with this -1. Why did he say -1 and not +1?
Because the other one is an upward.
Yeah. At +1, it's an open circle. The value does not exist there. It approaches that value, but it does not exist the actual value. So you're looking for where the filled in circle is. If we go across to B, what's f of -1?
4.
Ooh. You guys agree with 4? 4 because that's where the filled in dot is, yes? Filled in dot's totally removed from the rest of the graph. But it matters when they want the value. Now let's talk limits. The limit as x approaches 4 from the left. Thoughts? So we hop on the highway from the left as we approach 4. Where are we going to land? What are we getting close to? 3.
Can you say that again? Like 3.
Okay, so the limit as x approaches 4 from the left. So we're going to go to the left of 4 and we're going to get on the graph and we're going to approach. So as we get closer and closer to 4, so here I'm at the x value of 4, what y value am I getting closer and closer to? And that's 3.
How do you know to get on that line instead of the other ones?
Because here, well, so I'm looking for when my x is 4, which x is 4 is right there, yes? And so I'm in that area. In other words, I don't need to look over here. I just need to look around 4. And then the minus sign here says to go from the left. So I want to approach from the left, and this is the piece leading up to 4 from the left.
Okay.
Does that help some, Connor?
We get B.
B? Okay. So f of -1, what is this function when you plug -1 into the function? And when we look at x equals -1, here at 2 is an open circle. An open circle, the graph doesn't exist at the point -1, 2. My filled in circle is up here at 4. This is a very funky piecewise function. There's this line here, there's this curve here, there's this filled in dot, there's this open dot, and so you have to watch very carefully, which is stuff they're going to do. I mean, you have to be careful with your limits. Okay. Are we caught up for the moment? Maybe, maybe not. Okay. We're ready to try D? I would say try and stay a step ahead of me unless I get going too fast. The limit as x approaches 2 from the right. Get some of these extra pieces off here. So find 2 and go towards it from the right. If you're finding 2 and we go towards it from the right, what y value are we approaching? No? Not -1. +1? Why +1 as opposed to -1? Ah, okay. So, okay, here's the deal. As we approach 2, So that from the right means we're coming from here, yes? My first thought was Gracie just went from the wrong direction. But it's not that she went from the wrong direction. Here's the deal. What y value are we approaching? We're approaching that empty circle. It's a limit. The value does not have to exist at that point. It just has to approach and get closer and closer to that point. Okay, so now if I asked you what is f of 2, I agree, f of 2 is equal to -1. But a limit is as we're getting closer and closer from that side. And as we get closer to that side, it's leading us to this point here, which is 1. Okay? So a limit can be an open circle. It doesn't have to exist at that point, it just has to approach that point. Are we all clear on that one? Okay, let's try the next. What about the limit as x approaches 2 from the left? So what am I doing this time? As x approaches 2 from the left, what y value are we approaching? There's the -1. And this is a graph that is there's a discontinuity there. There's a jump there. Okay? F. As x approaches the value -1, from the right. As we go up here, we're approaching, it's an open hole again, isn't it? But that doesn't matter. We're just approaching it from the right. Are we getting a little better? Talk to me if we're not here. So that was as we approach -1 from the right, we're approaching this y value. Okay, what are we doing now? -1 from the left. So as we hop on the graph from the left, and as we get closer to -1, what y value is that? 2 again. -4 from the right. -4 from the right. 2. -4 from the left. The answer, I don't know. Okay, I'll take it.
Like undefined or something like that?
Okay, so the appropriate calculus answer is DNE. DNE stands for? Yep, does not exist. And why does this not exist? Yeah, my graph does not exist past -4. So I can't talk about the limit as we approach -4 from the left because my graph, there's no way to approach it. Okay, so at that point, D and E, and that's an appropriate, I mean, you can use that on AP Calc. Any calc person you talk to is going to know what D and E means. Okay. Okay with that one? Okay, J. What are we doing? X approaches -1. Notice, it's not from the left, it's not from the right. So what has to be true? Both ways, and they have to meet at the same place for this to happen. Okay, so as x approaches -1. So we're looking right in this area, yes? No, not there. Oh my goodness. Really, Amy? Okay. As x approaches -1, don't ask me, I don't know my values. So as we approach from the left, we're approaching right here. As we approach from the right, we're approaching right here. What value are we approaching? 2. And it was the same from both directions, wasn't it? So the answer is 2. Okay, what about as x approaches 2? It doesn't say left or right, so what's that mean? We have to look at both. So what do we get as x approaches 2 from the left? -1. What do we get as x approaches 2 from the right? +1. Are those the same number?
No.
No. So, guess what? Does not exist. And so this is part of the definition of a limit is if they specify just left or right, you get to answer just left or right. But if it just says the limit as x approaches some number, the limit from the left has to match the limit from the right. Otherwise, the limit does not exist. And so I don't have room. On my paper, I kind of squeezed it there in the blank. But the idea here is the limit as x approaches 2 from the left was what? -1. And the limit as x approached 2 from the right is +1. Right there, because those values are not the same, that's why it doesn't exist. Are we okay with that concept? That's a huge limit concept. L, the limit as x approaches 5.
Ooh.
-2.
It's not negative.
No. So it's the limit as x approaches 5. As we approach 5 from the left, what are we approaching here? That point -2, yes? Now, over here, it was an endpoint, yes? So we couldn't approach it from the left. What is actually underneath what I just drew? It was an arrow, yes? So does this line actually end here? No, it keeps going. So now, as I approach from the right, where am I approaching? That y value of -2. Okay. Limit as x approaches 0. Keep erasing this. As x approaches 0? Because 0 is the y-axis, right? So as we come from the left, it's approaching this -1. As we come from the right, it's approaching that -1. If it's a regular graph, there's going to be just an answer there. Limit as x approaches 1. Because again, you're approaching from here, you're approaching from here. It's happening at that point right there, -2. It's not hard. We just have to watch that. There's a lot of little things, aren't there? Or is it hard?
It's not my friend.
Not your friend yet?
No.
I like this stuff, but that's me. I don't know. Okay.
Could be worse.
It definitely could be
It really
worse.
could be.
It could be a lot worse. I mean, come on. It definitely could be a lot worse. So hopefully you'll make friends with this before it's over. Okay, at the bottom real quick, let's see, what's it say? I'm trying to remember. If we think of the function as a highway, then the point at 2, -1 could be considered the end of the road, while the point -1, 2 is more like a pothole. Okay, so 2, -1 is an end of the road. Like there's a dead end there, right? -1, 2, it's a pothole because the road keeps going, right? The road keeps going in turns, but there's a hole there. So a pothole is how she described it. Okay, how could you describe 2, 1? Okay, although pothole makes me think we keep going. Do we get to keep going?
It's like one of those things when they're,
Detour.
you're on like one of the big roads, and then it just stops and turns into like some other smaller road, and but the other there's another road with the same name,
It could be a lake.
not far from it.
You
That
just can't
you turn
cross
all
the
around.
lake. You have to stop.
I mean, that's the thing. Yeah, and so all that to say, I'm at some kind of dead end. When she filled it, when she talked about it, she put dead end without a barrier. You know, it's some kind of dead end because you're not going past that point, are you? Okay, it is, some kind of dead end there.
What do you mean we're not going past it?
Well, you're not going past it on that road. you stop. This does not connect to this. There's a gap there, right? It's like, I don't know, maybe if you go off-roading, you could connect over to here. But officially, this is a dead end. I mean, I'm not going to put it past some of you. Like, hey, I see where I need to be over there. Oh, there's just a field between me. Okay, let's drive through the field. Now I'm where I need to be. But that's what's here. There's a field between these two pieces, right? A dead end, there's a field between them. So, 4-3. What's 4-3? I don't know how. As I said, this is her, you know, we can come up with our own, but.
A sharp right turn.
Sharp right turn? Unless I'm coming from this way, that's a sharp left turn.
Just a sharp turn.
Okay. She called it a bump in the road.
I guess that would be like.
It's like you're.
I was thinking that
taking
one is
like
like
a
a
ramp.
ramp.
A ramp?
One that is like a big J.
So, I don't know what you want to call it. You know.
That's one heck of a breakover angle right there. My goodness.
I mean, yeah, that's those turns. It's the past the 90-degree turn that you're like, oh my gosh. So, okay, so yeah, I don't know. It is almost a U-turn, isn't it? Except we're not going straight back where we came back from, but it is almost like a U-turn. Whatever you want to, you know. We've kind of talked about them.
Is that going to be on the exam?
That's it, you know, as I get used to her notes, she throws some things in there just to kind of get you thinking, so. Okay, we've got some examples on the next page of some special cases. Case 1. Okay, so limits can fall into 3 different situations. This first case. Well, I'll come back to the name of it. No, it won't. I'm just going to, you know, limits differ on the left and the right is what we're looking at here. So as we look at an example, justify why the limit does not exist at x equals -1 for f of x equals the absolute value of x plus 1 over x plus 1. Here's my justification if I want to be official. The limit as x approaches -1 from the left. What is that limit? As x approaches -1 from the left? What y value are we at? -1. Okay. Now let's look at the limit as x approaches -1 from the right. So what about as x approaches -1 from the right? Where are we at now? We're up here at +1 level, yes? And here's the deal. This was asking us about the limit in general. It wasn't asking about the limit from the left and the limit from the right. So what do you notice? They're not the same, right? They're not the same. That limit does not exist. Good AP vocab setup. If we jump right into that from, where are we at? Day 2, day 3. The limit as x approaches 1 from the left of f of x does not equal the limit as x approaches -1 from the right of f of x. We have just justified why that limit does not exist. We showed the left-hand limit, we showed the right-hand limit, and then we stated that the limits are not equal. So when it comes, you know, way down the road, seems like way down the road at this point when we have to talk about May, but when we look at, okay, how do you support something in an open-ended question or free response? This is the type of thing you'll be looking for. You state the limit on the left, you state the limit on the right, and then you make a statement that they are not the same. Okay, case 2. Love that graph, right? Oscillating behavior. Okay, with oscillating behavior, justify why the limit does not exist at x equals 0 for f of x equals sine of 1 over x. And what's going to come down to is inspecting closer. We can look at the graph. Honestly, if I zoomed it in on my calculator, I had a pretty good view. And I could easily see why it wasn't working. Okay. Switch wrong thing here. I'm sure there would be no chance I'd happen to still have it in my calculator, would I? No, of course not. I was doing, because I was working on the whole. What is this one? Sine of 1 divided by x. So I know you can't really see that. Now, that's just a normal light, right? That doesn't tell me anything. That's worse than that. If I zoom in once, I'm going to zoom in and hit enter to get it to actually zoom in. Is it this one? Yeah, you can kind of tell there. What do you notice? From the left, it's going to some negative value, and on the right, it's going to some positive value. Is it connecting? No. And you could use trace. Remember how you have the trace feature to try and check that out? So, I mean, really it comes down to just looking, you know, by inspection. If we have to justify, just sketching a graph doesn't really justify. But what we could look at would be, what do I want to say? X equals like a negative 0.1 and a positive 0.1. So if you recall here, you remember how you can do trace? And I can type in a value. So I hit trace and I type in negative 0.1. Notice up there, I'm at positive 0.544, right? If I do trace and I type in, which one did I just do? Positive? So if I type in negative 0.1,
And you did negative.
oh, I did negative, okay. Obviously, I don't know what I'm doing. There we go. And if I type in the other one, right, it's now negative instead of positive. And you can go even smaller values than that, okay? But the fact that, how did I?
What does that mean?
Well, the fact that one is positive and one is negative, and they're not right at 0 yet, or right at something the same, they're not going to meet up. Like, that's helping to prove that those pieces don't meet up. Because sketching a graph isn't justifying something. Okay? We want to be a little more official than that. And so, since the idea, and actually I think, honestly, if I was doing it more official, I would go out farther. Rather than just do 0.1. Remember how we've been doing like 0.001, things like that? That gets us more official, doesn't it? And so, you know, like, what values? I have 0.001 written down. That this one's positive. And then I have negative 0.001 written down. Oops. And that's negative 0.82688. Well, I know those are getting close, but are they there? And we're already at what, thousandths? And you know, we got one positive, one negative. So those are almost 2 apart, and we're pretty much at 0. And so that's the type of inspection we can talk about. So here, what I can say is the limit as x approaches 0 from the, do I want to do left or right first? It doesn't matter, I guess. We don't know, we don't have an exact value necessarily, and we could use one of these values, but the idea is the limit as x approaches 0 from the right, it's going to be greater than 0, yes? It's going to be positive. Whereas the limit when x approaches 0 from the left is going to be negative. And if you have one positive and one negative, we can say, therefore, the limit does not exist. 3 little dots is therefore. Okay? Now, I'm assuming that's an official abbreviation. I just see it a lot on AP Calculus. But those 3 little dots are saying, okay, we said that this limit is positive, this limit is negative, therefore the limit does not exist. Because they're not the same, you know, they're not approaching that same value.
So is that an asymptote or does it not have a name?
It's not an asymptote. least I don't think it is. I'm not sure what it is, honestly. I don't have a name for it. I won't say there's not a name. I don't have a name for it. That's what I got you there. Okay? Okay, this is the one where I disagreed with the answer key when I was checking my stuff. And, okay, so the case 3 name here is unbounded behavior. Now, there's a technicality here. So, this says justify why the limit does not exist at x equal 2 for this given function. Okay, make the mistake I made. Because I made it, so I know you guys will make it. What would you say the limit is here as x approaches 2? Positive infinity is what I would have said, yes? Because the limit from the left is going up to positive infinity. The limit from the right is going up to positive infinity. And I think in some circumstances that is still true. Because I have seen limits like that depending on the situation, what we're talking about. Now, the official technicality here is, so we said our answer would be positive infinity. Infinity is not a number. It's a behavior. We're tending towards positive infinity. That's a behavior, and it's not a number. So if you recall, I made that note that L has to be a real number. The answer to a limit has to be a real number. And so in this case, that's why they're saying the limit does not exist, because it's behavior. Is that what I want to say there? Yeah. So by definition, infinity is not a real number. Infinity is a behavior of the function. Now, how do I want to write this? Is a really good question. Because I don't know what I want to write here. I mean, you can look and talk about the fact it's infinity from both ways. But the limit as x approaches 2 of f of x is infinity. But by definition, infinity is not a real number. It is a behavior of a graph. Okay, and again, it goes back to that real number piece from the other side that I mentioned. Okay. Okay. Can I finish this? I want to. We'll see what we can do here. Okay.
What did the ending say after it is not a real number?
It is a behavior of a graph.
Okay, thank you.
Even I look back to see what I wrote.
Mm-hmm.
Okay. Example 5. We're considering this function. Graphs are a big way to talk about limits. However, you will also see tables thrown at you. Tables like such that help you to find the limits. Now, you know how to find these f of x values, yes? You would plug them in, yes? Can I just write them in? AKA, can I just save us time? 0.1265, 0.125. Why do I have 0.1250 written down? Did I leave a number off? Maybe this one was supposed to be 0 also, I'm guessing. At 3, does not exist because it makes your denominator 0. 3.001 is 0.1249. Next one is 0.1248 and 0.12. 0.12334 is what I have written down. Close enough regardless. Okay. You magically, in like 2 seconds, completed the table by filling all that in your calculator, right? Okay. I'm trusting you know how to use the calculator. We've done a lot with the calculator, so I feel like that's easy. Now, we're trying to find the limit as x approaches 3. So, based on our analysis, what are the values of each of the limits below? So, this is asking, as x approaches 3 from the left. Where are we approaching 3 from the left? What's that? What am I looking at? Where's the left of 3? Number's smaller than 3, yes? So as we approach from the left, what value are we getting closer and closer to? And what value is that? As we approach 3, we're getting closer to the y value of 0.125. What is about as we approach 3 from the right? Now we're looking at the bigger values, right? So as we approach 3 from the right, so 0.1234, 0.1248, 0.1249, what are we getting closer to? I know at 3 it doesn't exist, but what value are we approaching? If you round it to 3 decimal places, it is indeed 0.125, isn't it? So if the limit from the left is 0.125 and the limit from the right is 0.125, what's the limit as x approaches 3? 0.125. Okay? So tables are definitely something you'll see when we start looking at AP problems. Okay? You'll see tables. We do a lot. They do a lot with tables. They love tables. Okay? Multiple choice, free response. So we have to be able to work with them. Although, in all honesty, the table would probably be filled out ahead of time. Okay, let's see. This was a picture. I'm trying to remember. So the idea, I keep talking about limit. It's not what is the value at that point. It's what are we approaching. And so she used this picture of the Hoover Dam being constructed and the fact that there's a limit here, right? There's a limit. Or in other words, a goal that they're trying to meet, you know, those two pieces of the bridge are trying to meet. That's their limit because that's their goal. They're trying to end in the same spot. And that's how she was kind of talking about a limit there. Now, limit existence theorem down there. Remember, we're finding the y value. This has kind of already been said. The limit as x approaches c of f of x exists if and only if. What are we saying here? The limit from the left equals the limit from the right, where L has to be, of course, a real number. That's what that is saying. It's in fancy terms, isn't it? But that's what you need to understand. The limit exists if the limit from the left equals the limit from the right, and it's a real number. Okay? Now, back page. So, in order for the general limit to exist, this was complete the sentence in your own words. Okay, what have we learned about functions? What did I just say down there? Yeah. Okay, the limit from the left has to equal the limit from the right. I've written down a function must approach the same y value from the left and the right-hand side. However, the y value may or may not be defined there, right? In other words, that y value may not exist itself, but the limit from the left and the limit from the right have to meet. Do you want me to do that real quick? I'm going to look at 7 in those sketches real quick because I'm more interested in those, honestly. I feel like we keep talking about this, so. Sketch a graph. You have a little bit of this in homework. So there's a point A that is undefined, okay? Here we go. Fancy graph. Got it? And I'm going to put point A is right there. A is undefined, so the graph at A is undefined. It's a hole, it's an asymptote, it's a jump, something. The point, it is a point discontinuity. What have I said point discontinuity is? That's another word for saying it's a hole. So there's going to be a hole above A. And the limit as x approaches A exists. So what's that saying about either side of the graph? They meet at the same place. They're going to meet at my hole. There's my random graph I drew. Does that make sense?
Yeah.
I put a hole on A because it said it was a or a point discontinuity. And then I made my graph exist, so it has to meet from the both sides. And that point is undefined, so there's a hole there. Now, this time, the limit does not exist at A. There is a jump discontinuity. So a jump discontinuity is like what we were seeing earlier where it's a piecewise. Yeah, like two different places. Okay, so think of a piecewise graph, and there is a defined point there. So the limit does not exist, which means my graph is two different places. There's a jump. Okay, so let's see. I'm going to make this go up here. I'm going to make this go down there, you know. Now, I have one other thing I have to do to make this true. My limit doesn't exist, does it? We're meeting at two different places. I have a jump discontinuity, so there's a break in the graph. It's a piecewise. F of A is defined. Right now, I have hole and a hole. What do I need to do to one of those? One of them needs to be colored in. Now does my graph exist at A? It does. I did that.
That was quick.
That was. Sorry.
Good job.
It's going to have to be that way some days, guys.
Miss Sargent.
I get that way in Cactus. I really do. So,
We do all of
Okay.
this.
yes, do your homework. Technically, if you look at the homework, there's 14 problems. However,
Tech.
Grass.
there's a bunch that like, okay, here's one graph and it has 6 different limits on it. Now, how long do the limits really take now that you know how to do them though?
Couple seconds.
I mean, they're not, I really think this is a, this should be
You look
doable.
fine. Yeah. Honestly, no one cares.
Yeah, I have a hole in my pants.
I feel like a sour patch in your shorts.
Yeah, there's like shorts underneath them though. But I ripped them on the side of the like chair at home.
Oh.
Yeah.